Dear students, today we'll see what do we mean by pulse width modulation, that is PWM. So here I have shown you an analog signal, which is the modulating signal or the information signal or the message signal, which will be denoted as XT. Then I have shown you train of pulses. This will be denoted as ST. Now all these pulses will have constant amplitude, constant width. This width is constant width, and constant position. From here it is TS time period, from here it is TS time period. So it is constant position. They are at constant position. So all this train of pulses are having constant amplitude, constant width and constant position. Now what we get here will be a pulse width modulated signal, and here the amplitude of the pulses will remain constant, the position of the pulses will remain constant. What varies is only width. Now according to the definition of pulse width modulation, the width of the pulses will vary according to the modulating signal. So according to as this modulating signal is varying, the width of the pulses have to vary. Now we will see which is the lowest voltage here. If you go on seeing, this is the lowest voltage, which is the lowest negative part. The lowest negative part, that is the lowest voltage. So here this width, what it was original, will become very narrow. You can see here it has become very narrow. And if you see the highest, this is the maximum voltage positive what we can have. So here what was the original width of the pulse, that has become more larger. The width has increased. That means as the voltage is going more positive, the width will increase, and as the voltage is going more negative, the width will decrease. So here if you see from the first sample, so this is having the original width. When it is coming here, the width is shown so much. As it is going more positive, the width is increasing. As it is coming down less positive, the width is again decreasing. As it has gone to negative, the width is decreasing. As it has gone to most negative part, the width is very much less. And as it is again increasing towards the positive, the width is again increasing. So here in this last wave, which is called as pulse width modulated wave, the width of the pulses is increasing or decreasing according to variation in the modulating signal. So as the modulating signal goes more positive, the width of the pulse is increasing. As the modulating signal goes more negative, the width of the pulse is decreasing. This is what we have in pulse width modulated definition. So it says that the width of the pulses will vary according to the variation in the instantaneous value of the modulating signal. So this is your pulse width modulated wave or PWM wave. Dear students, here we see today the generation of PWM output. For a generation of PWM output, we require a comparator. And the two inputs of this comparator are the modulating signal, the analog wave, and a ramp wave, that is, this is the ramp wave. Okay. Whenever these two signals intersect each other, the output of the comparator is going to change its state. Now, one more condition is there. If you name this analog wave as XT, and if you name this ramp wave as ST, then whenever XT is greater than ST, the output will be more positive. Similarly, whenever XT is less than ST, the output will decrease. It will be less positive. It will go towards negative. Okay. So here if you see at the point of intersections, you can draw this output wave. You can draw this output wave of a pulses. Now in this output wave, the amplitude of the pulses will remain constant. You can see the amplitude remains constant. The time period between pulses, that is the position of the pulses, will also remain constant. What will vary is the width of the pulse. Because of the intersection of the ramp wave and the modulating signal and the output of comparator. So whenever the analog signal is greater than the ramp wave, it is going more positive, the output of the comparator will give a pulse which has more width. Similarly, whenever analog signal goes negative, its magnitude is less than the ramp wave, the output will give a width which is more smaller. It is smaller. It is not going to be big. It is going to be small. So this shows that whenever analog signal is going more positive, the output of the width output of the pulse is more. And similarly, whenever the analog signal is going negative, width of the pulse is less. That means the width of the pulses is varying according to variation of this analog signal. So we can call this as a PWM output, pulse width modulated output, where the width of the pulses are becoming more or less. They are varying according to the instantaneous value of the modulating signal or the information signal or the message signal. Okay, so this is your PWM output. So we have generated the PWM output.